Board. All right. Okay, so this is the review session. We're going to be going over the concepts we learned in Physics 7b. This is going to serve as a broad strokes overview and summary of all of our major concepts. So we've taken a vote, and the starred concepts are ones that are especially popular, ones that we feel least certain about. So we're going to spend a little bit more time on those. What I'm going to do is I'm going to go through each of these elements listed, each of the items, and I'm going to ask your questions at the end, but also if at any point there are questions along the way, please do break in, either with chat or with audio. Because I'm going to be mostly looking at my Zyboard screen, I may not catch all the chats immediately, so if there's something like pressing, just unmute for a second, it's no big deal. Interruptions welcome. Okay, so let's start off with the first thing. First things first, fluids. So there are basically two equations that we emphasize when we talk about fluids. So I'll write those equations and then I'll describe what each of them means. So, hello, let's move this over. Sorry, doing digital management here. All right. Okay, so the first equation to talk about in the context of fluids is Bernoulli. So Bernoulli's equation. So Bernoulli's equation is written as the change in pressure between 2 points plus the change in height between 2 points scaled by density times gravity plus 1/2 the kinetic term, which is the density times the change in the square of velocity. Hello, come on, Zyboard, giddy up. V squared is equal to the energy input by the pump per unit volume minus the current times the resistance, the resistive term. So each of these terms represents an energy density. So an energy density here meaning an energy per volume. That's an energy density. So each of these is an energy density. The pressure term tells me about the energy associated with, say, like the particles hitting the walls, just how tightly compressed my fluid is, something like this. The height term has to do with the gravitational potential energy. And this term over here has to do with the kinetic energy. So a density is mass per volume. So this is kind of like mv squared, 1/2 mv squared. This is a kinetic energy term. It has to do with how quickly the stuff is moving. There's a pump energy associated with a change, an increase or decrease. Well, it has to be an increase in energy flowing downstream associated with a pump between 2 points. And we've got a resistive term, which is the energy dissipated by friction in our fluid system. So the most important thing to understand about Bernoulli, like the terms are all nice to understand, but the most important thing to understand is the significance of the delta. What do these deltas mean? So Bernoulli's equation, as we've written it, says in words that the energy density of a fluid system in equilibrium is constant everywhere. So that's what I say in like big semi-fancy physics words. The energy density of a fluid system in equilibrium is constant everywhere. What that means is, if I've got a fluid system, whatever, kind of whale-shaped. If I've got a fluid system and I want to consider 2 points in it, say that the flow is going this way, and I want to consider 2 points in my fluid system, both of these points have the exact same energy density. So changes in the energy density, sum to 0 if the fluid system's in equilibrium. These two things represent like changes in that energy density. So if I throw a pump in there, I'm kind of keeping it away from equilibrium in the sense that my pump is throwing in some energy that wouldn't exist otherwise. The resistive term pulls energy away. Okay, cool. So the delta refers to the, say in delta P refers to the pressure final minus pressure initial. So the delta P would be expanded out as pressure at the final point minus pressure at the initial point, and so on for the rest of these. This is probably familiar. I think overall we're mostly comfortable with Bernoulli's, but there it is. That's Bernoulli's equation. that's basically all I wanted to say for now on Bernoulli's equation. Is that okay? We got questions about Bernoulli? Real quick before I hop down to continuity. I'm going to start writing for continuity, but please do ask questions about Bernoulli if you like, verbally or chat. Okay, no questions so far. Hard to say if that means bored or just convinced. So, all right. So let me know. The next major equation from continuity, or from fluids, is the continuity equation. So what the continuity equation says in words is that the fluid volume per unit time is conserved. What does that mean? It means basically you can't spontaneously, you can't magically create or destroy volume of a fluid, of an incompressible fluid. So particularly this applies really well to liquids. It's probably a better thing to say, but whatever, it's fine. You can't magically create or destroy volume of a fluid. So in particular liquids, because gases you can change the volume, but whatever. We deal with fluids like liquid fluids in here. So what current is this I is a volume per time. And what current describes is the amount of stuff passing through a given region of my fluid circuit. So say this is a pipe and I've got some, I've got some current flowing through it. Then one way that I can measure the current is by taking a cross section and saying, okay, what's the velocity of fluid flowing through this? The velocity of fluid flowing through this. If I multiply those two numbers together, I'll get like an effective little cylinder. This is kind of like unnecessary geometry, but maybe to help build the intuition. If I multiply those together, I'll end up with a volume. So it's a volume per time. This volume of the cylinder characterizes the flow. If I have a larger velocity, then I'm going to end up with a larger flow, a larger current. I'll do it in a different color. So it tells me basically, the current tells me basically how much volume, how big the cylinder is, of water transports in a given length of time. So if that's confusing and you already have a good built-up understanding of flow, don't worry too much about it. Of current, don't worry too much about it. But that's how I think about it geometrically. It's this little. It tells me how much the volume of the fluid that's moving a given area of pipe at a certain time. And what continuity tells me is that if I take this point in my pipe, or I take some later point in my pipe, say over here, maybe it gets wide, it tells me that the volume of water passing through any surface is the same. So in this case, the velocity will become smaller because, if I've got a skinny cylinder versus a really wide cylinder, in order for them to have the same volume, it's got to have a shorter length. So the velocity, the little red vector here, is going to have to be smaller in regions where I have a wider pipe. That's fluid continuity. In words, I say you can't magically create or destroy volume. With a little bit of math, I say basically the area times velocity at any point is constant in a leakless circuit. So note that this is only true. Continuity is only true when there are no leaks between point 1 and point 2. So as a counterexample to that, if I had a second pipe that kind of branched off from my first, so if you like a junction that branched off from my first, well, now if I consider the fluid speed over here to the right of my initial point, well, now continuity is no longer present because there's a leak. There's somewhere else for the volume to go. So the fluid volume is not conserved from 1 to 2. There's a leak. There's somewhere else for it to go. So if you ask, continuity only works for steady state systems, right? There's a more generalized sense of continuity that works for non-steady state systems. but this exact expression only works for steady state systems. That's right. Yep. Thanks, Sophia. Okay, that's all I really wanted to say about continuity. Any questions on continuity? What's it mean? Let me get some thumbs up, thumbs down. Use those reactions. How are we doing? Is this okay? Give me a clap if you want to speed up. Give me a thumbs up if you're like, this is all right. Give me a thumbs down if you're like, I'm okay with the speed, but I really don't like this content / I don't understand it. I don't get it. I don't remember this.
Sorry, I had a question.
The original series and the reboot take place in the same multiverse. Yes, it totally makes.
Okay. Cool. Fair enough. If we just look at the second pipe, would continuity still apply? So Vishal asks, if we just looked at the second pipe, would continuity still apply? So when I say continuity here, let's go ahead and make sure I get this out of the way. So continuity could still apply if I took into account both areas and both volumes. So like the volume encompassed in this little cylinder, this little section of volume that's traveling along, that volume is going to split into two parts. So I can keep track of both of those areas and both of those velocities. Oops, someone had a question on unmetered decay from volumes all the way up. Hello, 1 sec. Sorry to whoever I interrupted. Sometimes my my Bluetooth speakers act up, Bluetooth headphones act up. Again, help me out. Was there a question?
So could you say what steady state is again?
Yeah, sure. So steady state means a current is constant. Steady state means current is constant. So yeah, steady state, constant current. So an example of non-steady state flow is when we've got those two standpipes and they're at different heights and they communicate through that little resistive pipe in between, and they kind of eventually have to level out. Good question, thanks.
Does a pump or resistance, I guess, stop it from being in steady state? Yeah,
so no, is what I would say. A pump and a resistance don't stop them from being steady state. There's a chance that I misspoke before. What I would say is that, like, if I want to get really nitty gritty, pumps and resistance make the system, in a sense, non-equilibrium, in the sense that, like, two different points in the fluid can have different energy density at that point. So, and this is kind of, again, splitting hairs. So don't, if you're not tracking with this, it's not a huge deal. But say that I had some current flowing this way, and I have this pump, which is, there we go, now properly a pump. So if I have these points 1 and 2, and the pump is inputting some energy, then the energy density on the right, yeah, is greater than the energy density on the left. Yep, that's true. So it's non-equilibrium in the sense that I have to kind of keep some energy going in order to keep the flow the way it is now. So when I push this pump in here, I'm adding in some energy all the time. And that represents, strictly speaking, a non-equilibrium state. So if I have to add energy to keep something going, that's non-equilibrium state. Yeah. However, it's still in steady state in the sense that the current is not changing. Yeah. So non-equilibrium means I'm adding energy. Steady state means I am at a constant current. So when I throw a pump in there, strictly speaking, I would call this a non-equilibrium steady state flow. But that's kind of like, who cares?
Okay, so yeah. Adding the pump, the current would still be the same at 1 and 2, but
that's right.
Would something like the pressure increase at 2?
That's right. That's right. So what a pump typically does is it's going to increase your pressure. That's the most direct thing it does. Yep, that's right. So between point 1 and 2, if there's nothing else in the way, if I were to kind of apply my Bernoulli equation, there's a pump in the way, so that stays. Let's just assume there's no resistance. It's not relevant for us to think about right now. There's no change in the area of the pipe, so that one's not here. There's no change in height. So the most direct thing a pump does is change the pressure. Yep. Does that help?
Yeah, thank you.
Yeah, good stuff. Thanks for the question.
Hi.
Yeah.
I have a question about the continuity equation.
Go for it.
So, I get confused like when we would use the formula for the area of a circle in that equation.
Yeah. So the area thing, the area has to do with the cross-sectional area of the pipe or fluid system you're dealing with. So like you can imagine, maybe instead I'm talking about a semicircular river. I can't draw this that well. Let me try again. You can imagine that maybe I'm thinking about instead a semicircular river or something. This would be my area if the river is flowing, say, this way. Nice river. And we got, I don't know, let's say some grass out here and on this side. So this is my area. It's the cross-sectional area of whatever is carrying my fluid. That's the area. So typically pipes, when we say pipe, in physics, we assume a pipe is a circular pipe. So if you have the radius of a circular pipe, you could then calculate the area of this circular pipe. Does that help?
Yeah, sorry, I was just like confused because there's like some like problems when we didn't have to use like pi r squared, and then there's like other problems when we did. I was just like confused like when we would apply that.
So yeah, sometimes they'll just give you the area directly, in which case no need. Sometimes they'll give you the radius. Yeah, it kind of just depends on what you're given, or the diameter for that matter.
Okay, thank you.
Sure. Whitney asked, one of the practice questions, a question asked if the current increased from point 1 to point 2, and the answer was yes, due to dissipation. How does dissipation increase current? Weird. Let's think about that.
Isn't dissipation R?
Yeah, dissipation, right. Dissipation is typically taken to mean either this whole term or just the resistance term. How does dissipation increase current?
Did it say like maybe
So-
the left side of the equation, both problems was the same?
Sorry, I didn't catch that. But to answer the question more generally, in general, dissipation doesn't increase current, I wouldn't say. If anything, if I increase my resistance, then my current will decrease typically. If everything else in my circuit is held the same. Maybe that's a good thing to talk about at the very end. It sounds like it could be a particular thing, but in general, dissipation doesn't increase current necessarily. They're not. It's not like a simple one-to-one relationship. Part of the reason that this is complicated to talk about is because I've got like 5 different variables here. So changing any one variable, it's not immediately clear what other variables are going to change. Each of the 4 remaining variables, if I change one variable, could change. It's going to depend on my system what is allowed to change. So if I have just a pipe system, and I don't change the geometry of the pipe system, then between any 2 points, delta y is going to stay the same regardless of what else I do. But if I have like a river where maybe I increase the amount of fluid that's flowing through it, well, that's going to change the height of the river. So yeah, there can be a difference. Okay, I'm going to go ahead and say, let's make a move on from fluids, just because, it's almost a half hour in. Probably need to get a move on. But we can return to this hopefully at the end if there's time. And if not, happy to talk about it afterward. Okay, let's head over to electrical circuits and Kirchhoff's laws. So, to electrical circuits and Kirchhoff's. So electrical circuits, there's a couple of elements that we can talk about in the context of electrical circuits. The first is a resistor. It's something which dissipates energy by usually as heat, but we don't typically care too much about that. It's just something that dissipates energy. Another thing that often acts as a resistor is a light bulb. There are batteries, which we typically draw like that. The positive end of the battery is the longer end, the negative end of the battery is the shorter end, and it applies some constant voltage to a system. There are ammeters, which are used to measure current, and there are voltmeters, which are used to measure voltages. Okay, practically, and there's also, I'll save this for later, but there's also capacitors, C. This is labeled R, this is labeled uppercase script E. So capacitors we'll save for later, but this is another common circuit element. The last thing I want to mention is that circuits often contain switches. which if I close this switch, if I make it so that the two sides are connected, I say that I close the switch, which allows current to flow. Okay. So, two main equations here. There's the Kirchhoff voltage law and the Kirchhoff current law. So what I will do, and there's a couple of other follow-ups that are kind of minor, but let's just put these ones down. So let me give an example circuit just so that I have something to talk about. So let's say I have something like this. I've got battery, and let's just say it's two branches, a resistor on one branch, a resistor on the other branch. Boom. Hang on, monitoring the chat. Make it hard, lol. Nah, I'm not doing it. We're doing a simple circuit, but it'll demonstrate the concept. Actually, I'll tell you what, I'll make it a little harder. I'll make one of the sides of this branch have two resistors and the other have only one. Okay, so Kirchhoff's voltage law. What does Kirchhoff's voltage law say? Kirchhoff's voltage law says that when I go from one point in a circuit back to itself by taking any loop, final, Kirchhoff's voltage law says that the change in voltage around a loop is zero. In other words, the sums of the change of voltages of all of my circuit elements around that loop are zero. So in the context of this little pink loop, that would mean that the change in voltage across the resistor, that's the first thing I hit on my path, plus the change of voltage across my battery is zero. Nice. Okay, so that's the first Kirchhoff law. I can imagine doing that for any of the loops of my circuit. Usually you want to start your loop with a battery. You don't have to, but usually that's convenient to do. Whoa. Did my internet just freak out? Y'all still there? Good?
Yes.
Okay, cool. Tell you what, actually what I'm going to do, I'm going to get my hard connection. One sec. Have I been breaking up at all so far, or has it mostly been all right?
It's been okay.
All right. Let's dive back in. Okay, so there's Kirchhoff's voltage law. If I draw a loop and I say hello to each of the elements I hit on my way around, this resistor, and the battery, delta V R1 plus delta V R2 plus delta V battery, they'll sum to zero. And I can do that for any closed loop around my circuit. Nice. Okay, the other Kirchhoff's law is the current law. So in case it's not obvious, the equations that I think are important are ones that I'm boxing. So if I put the little brackets on them, that means I think they're especially important. So Kirchhoff's current law tells me that the current into a junction is equal to the current out of a junction. So for example, in this simple circuit I've drawn, the battery is going to drive current this way. Then it has the option to split into two parts. So I'll call this one I battery, I1 and I2 at this junction. Boom. So in the context of this problem, it tells me that the current entering the junction is equal to the current exiting the junction. And maybe now's a good time to just back it up and say in general, like what these things are, voltages and currents. So, because I know that sometimes gets swept under the rug. So what a voltage is an energy per charge. So it's an energy per charge carrier. Chargers are swirling around the circuit. Voltages tell me the energy of a collection of charge. Current tells me how much charge is flowing past a given point. So it tells me how much charge is flowing past a given point. Yeah, so the thing to think about here is charge is kind of like volume in our fluid case. Current is like charge per volume, which is kind of, or charge per time, sorry, which is kind of like volume per time. Voltage is like pressure, which is like energy per amount of thing, energy per volume or energy per charge. So those are kind of the parallels we want to draw. This part tells me about changes in pressure. This part tells me about, it's basically an expression of continuity in the sense that it tells me that current must be conserved. I can't spontaneously create or destroy charges. So these are just like the Bernoulli equation and the continuity equation, respectively. These are their electrical analogs. Okay, I know I've been talking for a while. Do we have any questions about Kirchhoff's laws off the bat? and then I want to give a couple other like kind of ancillary results.
Hey, I have a question.
Go for it.
So if you had your currents, like how you're drawn in the circuit, but let's say for I2, there was no resistance. So you basically shorted
Yeah,
that on that
sure.
side. So
Cool.
is that the only time when you can say that there will be no current flowing through I1 when you short that junction?
That's right. So the only time you'll have a region, well, okay, so there are two, I guess I'd say typical cases when I would have no current through I1. One is when I1, like this like rightward branch, I'll call it, is effectively disconnected. So if I've got something that acts like a switch that disconnects that side, that's one case where I'd have nothing going through there. But also, yes, if I short the circuit, if I short across that area, then the effective resistance here is 0. The effective resistance here is 0, which makes the equivalent resistance of this overall thing also 0, if I were to try to calculate the equivalent resistance. So long answer turned short is that yes, you'll have no current flowing through this other one because I've shorted across here. So there's a common misconception that sometimes people carry into the final, which is that like current always takes the path of least resistance, as in all of the current goes into the section that has least resistance. And that's not true. The current splits into regions that have differing resistance, but it's like proportional to how resistant each side is. So it will tend to go the least resistive route, but it doesn't all go down that route. In the case where there is a branch of the current which has 0 resistance, all of the current will attend to that because it's proportional, or I guess you could say it's inversely proportional to the resistivity. So if I have 0 resistance, that's like 1/0 means, all of the current will go that way. But that's the only case where all of the current goes into one branch, is when that branch has 0 resistance, or when the other one has infinite resistance. Yeah, thanks for the question. More questions. These are good so far.
So I have a question as well.
Yeah.
So if you have like all like the and not like all of the resistors and stuff,
Yeah.
and like say like you had like that parallel again, and so can you find the current in like can you find the total current first, and then can you like separate the loops, I guess, to find? I'm sorry if this like question doesn't make any sense.
I think I think what you're getting at. Are you asking like how would I go about finding each of the individual currents?
Yeah.
Yeah. So there's a couple of ways. I think the easiest way, the one that's going to be least computationally expensive in terms of like your time, is to find each of the currents by applying the loop rule. So you do the pink loop and the blue loop. Once you have those two, you know the currents through each of these, I1 and I2, and the sum of those has to be the battery voltage. So that's fine. You could alternatively find the total current out of the battery by reducing the capacitor, reducing the resistors. So doing those resistor additions to find equivalent resistance, and then determining the battery voltage. Do one of the loops, that'll be the last one, the last current. So like either will get you there. For me, what I think is fastest is to do the loop on each. Yeah, the two loops, the pink loop and the blue loop. Does that kind of answer it, or is that still a little iffy?
No, that's perfect. Thank you.
Yeah, sure thing. But yeah, if all the resistances are known, you can always find the currents and voltages everywhere. There are some particularly nasty circuits where it's hard, but we don't do that. Yeah. Kate asked, at the initial moment when you place a capacitor, current is 0 through I1, right? We'll get to capacitors in a minute. Hang on, I'm holding off on that. Okay, so there we are for currents, or for circuits. It's 4:37 now. I'll take 3 more minutes to brush through the 2 remaining major concepts I want to talk about. The first one is Ohm's law. So Ohm's law says that the voltage across a resistor, the change in voltage across a resistor, is negative current through that resistor times the resistance of that resistor. So it describes the situation where I've got a resistor. It's got some change in voltage that I can measure with my voltmeter or whatever, and it's got some current going through it, I. And here's my resistor value R. Okay, so I have to refer to the current through the resistive element. That's the main thing that is like sometimes trips people up about this equation. So there's a change in voltage across the resistor. The change in voltage from one end of the resistor to the other is the current through that resistor times its resistance. It tells me that basically the more current I have, the more energy will be dissipated by the resistor. Yeah, the way I think about this in terms of like things that I encounter on the daily is like if I move my hand slowly across a table, it only heats up a little bit, but if I move it along quickly, it heats up a lot. So that's how I think about resistors more intuitively. The faster my movement, the faster the movement of charge, the more the energy gets dissipated across that resistor. The more energy gets lost.
So a quick question.
Go for it.
Is current shared by all resistors in a series?
The question is current shared by all resistors in a series, right? Yeah, that's true. So if the question is all current shared by resistors in a series? So if I've got like several resistors that are all in series like this, if all of the resistors are in series, like perfectly in series like this, and I measure the current over here to be I1, and I measure the current over here to be I2, then the current I1 is equal to I2. And it's the same at any point. Like if I measure the current at any point in a series area, the current would be the same. This is the simpler version of continuity to speak about. Yeah. You can't spontaneously create or destroy charge. Good question, thanks. Does that help? All good?
Yeah, it does. Thank you.
Yeah. Okay. Now the other thing that I wanted to talk about that was just kind of a quickie equation is if I've got a section of circuit, that acts as an equivalent resistor, then I could talk about the power dissipated by that circuit, which is energy per time, the power dissipated by that circuit as delta V times I. That's the power dissipated by a section of circuit that can be treated as an equivalent resistance. So delta VR times I. Yeah, maybe that's the best way to put it. So if I've got some chunk of my circuit and it's got who knows what kind of ugly resistor thing inside, gross, all right, and I come out the other side and I've got a change in voltage across that, and I know how much current is going in, I know the power dissipated by this element. Delta V times whatever that current is, I. We see it first in the context of a single resistor. So if I've got a single resistor, I just put subscript R on everything. It's the change in voltage across that one resistor times the current through that resistor. Yeah, that gives me the power. I can use Kirchhoff's law to get different expressions for the power. So if I substitute in for delta V or substitute in for I, then I can get expressions for it that are like only in terms of V and R, say, or only in terms of I and R. And those are all included on the equation sheet. But if I want to find the power, this is the fundamental thing. It's energy per charge times charge per time. So energy per time is the units you get out of that. Okay, that wraps up, I think, the main thing to talk about for circuits. The very last thing I want to talk about are the two options for resistor addition. Keely, a question, go for it.
Hey, sorry. Back to the loop rule.
Yeah.
Because you mentioned like when there's a resistors in series that the current throughout would remain the same, but
Right.
I remember doing like a problem when like the circuit looks like the one that you did in pink. And
Yeah, up here. Sure.
yeah. And then when I did like the loop rule for like each circuit, the
Yeah.
current isn't the same.
That's right. That's right. So what I'm saying, when I say the current through resistors in series is the same, in this example up here, that would mean that the current through these two is the same. These are two elements which are connected perfectly in series. The tail of one leads directly to the head of the other. So they have to share their current. It's not true that the current through, say, I'll put it in orange, these two circuit elements is the same, because in between the tail of one resistor and the head of another, the 2 points where they connect, there's this little junction. So the current can split off, so to speak, at junction points. So if there's a junction in between two circuit elements, all bets are off as far as continuity goes. Or I shouldn't say as far as continuity goes, but in terms of them having the same current. If there's a junction, it's kind of like having a leak in your pipe. Current doesn't have to be conserved between two things that aren't in series. Yeah. So like these two aren't in series. So the current is not guaranteed to be the same.
Okay, yeah, that makes sense. Because when I did, yeah, never mind. Yeah, thank you. That does make sense.
You're good. Yeah. Did anybody else see some lag there? Anything I need to say again? Can't you find the ratio of current flowing through each by finding the ratio of resistance? Yes, that's equivalent. Yep. So I don't want to hang on. I don't want to confuse too many people, but Whitney, yes, that's equivalent. It's the same way. It's equivalent to finding the equivalent resistance, churning through those extra equations. And in terms of like numbers to crunch, it should be basically identical. Like I don't think there's a whole lot of time saved there, but it is an equivalent mathematical procedure. Good question, thanks. Okay, very last thing to talk about on circuits before I breeze on to the next topic, exponential decay, is series and parallel. So if I have two resistors that are in parallel, so perfectly in parallel means that the head of one resistor is attached to the tail of the other, then the equivalent resistance, if it was just so if I were treating it as just a single resistor, is given by the sum, R1 plus R2, for these two resistors. Now, parallel, the other one, is when two tails of resistor are attached to one another and two heads of those resistors are attached to one another, like that. Okay, so this is an example of a perfectly parallel set of resistors. The equivalent resistance of two resistors in series is the inverse of the inverse sum of resistances. Yeah. Yep. Or another way to say this is R1 to the -1 plus R2 to the -1, all that to the -1. Whatever way you like to say it. I think this one's prettier, but it also, I don't know. You have to remember all your -1s, whereas here it's like fractions are more obvious. Okay, so those are series and parallel resistors. Usually we do resistor reduction with the goal of finding the either the total voltage across that area or finding the battery current. Usually that's why we end up doing resistor reduction. Yeah. Cool. What else? What else? What else? Masha, I think, help me with pronunciation if you like, asks, resistors in parallel always have the same change in voltage, right? That's right. So if I've got two resistors in parallel, the change in voltage across them must be the same because the voltages at either side must be the same. So like we have V1, V2, V3, and V4. Delta VR1, the upper resistor, has to equal delta VR2 because delta VR2 is just V4 minus V2, and delta VR1 is V3 minus V1. And because these 2 points are connected by a wire, V1 and V2 and V3 and P4, those are the same. So this is really V4 minus V2. So trivially now, they are equal to each other. Yeah. So because the tails of the resistors in series are attached to one another and the heads are attached to one another, the change in voltage across them must be the same. Two branches that are a branch that is in parallel with another branch must have equivalent voltage changes across either branch. Thanks. Okay, 447. Probably time for us to move. We should hit exponential decay. So let's hit exponential decay for a sec. So exponential decay, there's two forms that we looked at for exponential decay. Exponential decay is our hallmark example for non-steady state flow. Non-steady state flow. So non-steady state flow, meaning that current is not constant. Current is not constant. Current is a function of time, as opposed to just being independent of time. Okay, so current is a function of time. So exponential decay is characterized by the exponential curve. So typically, we see exponential decays. We see things that start at some finite value. I call that, say, x naught. Here's x, here's t. And over time, it will exponentially decay. Let's see how good of an exponential I could draw. All right, it could be worse. It'll exponentially decay to some other value. Classically, it's just 0, but like in general, you don't have to decay to 0. You can decay up or decay down to any like number. But so the typical exponential decay looks something like x as a function of time is x naught times exponential of negative t over tau, where tau is, we call the time constant. Time constant. Okay, so the time constant is basically how long it takes for, what is it, 77%, something like this? 70, some percentage to decay, for us to lose that amount. So let me double check myself here, make sure I got the right number. 63%. Yeah, you're right. Thanks, Alice. So 63% to decay. So like maybe down here, this is when I have 37% remaining, or yeah, 37% remaining of x naught. This would be the distance associated with tau. That's just one tau life. When I go another tau, that's going to be 37 times 0.37 times 0.37. It's around 13%. 0.13 x naught, and so on. So that's 2 tau. So every time I go forward a time constant, I lose 63%. Often we'll talk about this instead in terms of the half-life, because half-life is a little bit more intuitive. So the half-life is when you go 50% each time. There's t1/2. And then here's 25%. Here's 2t1/2, and so on. So the distance between subsequent half-lives should be the same. So this time value should be t1/2 constantly. This distance between them should be the same. I've probably misdrawn my exponential decay a bit here, but they should always be the same distance away from one another.
Sorry, what is the next number after 50? Or like the next orange number?
Sure, this is 25%. I think I
sorry.
tried to make my percent too big. You're good. 25. Hello. All right, it's not going to work for me, but it's half of 50, so 25%. Okay, so the time constant refers to a time, and in particular, it's the time it takes for me to decay by 63%.
I'm sorry, is that
Go for it.
that second green number is 13%?
Yes, 13%. So it's 37% times 37%. 13%. Yeah, or 13.7%, I guess technically, but you know, yeah.
Can you explain how you got the 63% from the?
Yeah, sure. So
Thank you.
without going into like a ton of detail, I'll do it like this. So the time it takes for a half-life to happen, in terms of the amount, I don't know how to say this well. Let me back up for a second. Okay, in terms of the how much do I lose? How much of X do I lose for a given tau sub number? For a given tau sub number. So t1/2, I lose 1 minus 1/2. Or that, sorry, this is the amount that remains. No, I'll say it's how much I lose. So this is the amount that I lose. I lose 1/2. So if I say 1 minus 1 over e, which is 1 over e is the value for which, how do I say this well? when t equals tau, this thing becomes 1 over e times x naught. Yeah. So when t is tau, at t equals tau, the right-hand side is x naught over e, the Euler's number, Euler's constant, question mark. So that's why here this is an e. I don't want to belabor this too much because it's not really a huge deal, but basically the time constant refers to the time constant turns out to be 63% because at this point in time when t equals tau, we have 63%. We've gone 63% of the way to our goal, leaving 37%. This is around 0.37. So that's sort of where those numbers come from in a hand wavy way. Similarly, when t equals t1/2, we've gone halfway to our equilibrium value, gone halfway to whatever we're decaying to. Does that help a little bit, or is it kind of still iffy?
Yeah, I think it's good. Thank you.
Okay, yeah, sure thing. Okay. So I'll wrap this up by 5 so that we still have an hour left for the remaining things, some of which is somewhat familiar. Okay, good. So there are two main systems we use to talk about exponential decay. So the first one is a capacitor. So if I've got a battery or just some change in voltage, something which supplies my capacitor with voltage, be it a battery or a resistor that has some voltage difference across it, whatever it is, it's effectively a battery supplying some voltage. The capacitor will charge up, and I need a resistor here too. The capacitor will charge up to some maximal value. So the capacitor, say it's initially uncharged, its voltage is 0, delta V across the capacitor is 0. Over time, it'll reach the battery voltage. So here's my battery voltage E, there's time. The time constant for a capacitor is RC. So this is an RC circuit. The effective resistance R is given by this resistor. The capacitance is given by the capacitor. So it's independent of the battery voltage. The time constant is independent of how much current I give it. It's just dependent on the resistor and the capacitor. Let's see, what else? Go for it, question?
I just had a quick question.
Yeah.
So for the R in tau, is it R equivalent or just one R, or like what is it?
So yeah, so it is the equivalent resistance of whatever is standing between the voltage source and the capacitor. So I can imagine, for example, I don't know, I can imagine having some complicated, maybe like this. Here we go. We've got 2 resistors now. So now in the same loop as the capacitor, in the same branch as the capacitor, I guess is a better way to say that. No, I'll call it a loop. In the same loop as the capacitor, I've now got these 2 resistors. The equivalent resistance, since these resistors are in series, is their sum. So R equivalent would be like, I'll call this R1, R2, R1 plus R2. And then in my equation for the time constant of the circuit, I would use the equivalent resistance. So tau would be R equivalent times C, which is R1 plus R2 times C. So what I would say is the time constant of a capacitor, of a resistor capacitor section of a circuit is given by the equivalent resistance of that loop. The equivalent resistance of that loop.
So if
times the capacitance.
another loop with
What was that? Sorry,
so
I
if
lost
there was
you.
another loop
Yeah.
with the
Another loop, like say
resistance,
here?
like let's say yeah, for example.
Something like that.
Yeah, like basically where it was like in parallel with the capacitor.
Yeah.
And so would we include that new resistor or no?
So no. Yeah, not for this thing. No. So I think maybe what you're originally saying is something like this. And what I'd say
Yeah.
about that is that we will not do that to you. so you don't have to worry about something quite like this, because it's a bit more complicated. Yeah.
Cool. Thank
Yeah, but if we had something like
Thank you
this,
very much for that.
yeah, sure thing.
Adam, I just had a few questions. The first, like, I remember in the beginning with like when we were starting exponential decay, there was all this information about how like the decay rate is independent of area, but I was just a bit confused about that because like I thought the decay or lambda was PG over AR. So even if you're canceling out of the equation itself, it's still in the exponent. So like would that not be influencing the decay rate?
So let me refresh myself here. You're thinking about so now we're transitioning over to the fluid system. So we've got a fluid system, has some area. There's some water level X, or I guess I'll say delta X is the difference between the two water levels in our two sides. Here's my second height. Here's my delta X, which will change as a function of time. And the middle section of the pipe is a bit rough, so we have some resistive section in between. So what you're referencing, I think, is the time constant for the fluid case, which is AR over rho G, which in terms of lambda, let's see, what's that going to be in terms of lambda? I have to kind of always think about it. It's just going to be the inverse of that. So the lambda, the rate for my fluid, is going to be rho G over AR. There we go. Okay, so now I'm ready. What was the question?
Also, if you want, you could like go into this after you do capacitors. You don't need to jump around.
Yeah, okay, I'll come right back to it. Let's see.
Sounds good.
We've got one quick question in the chat about capacitor. Can you briefly go over Q graphs for discharging versus charging capacitors? Yeah, sure. So this is what I'd say is the charging of the capacitor. The defining characteristic of the capacitor is its capacitance, which I'll box this. C equals Q over V. Yeah, Q over delta V. There we go. So the capacitance refers to a capacitor's ability to store charge for a given change in voltage. Its ability to store charge for a given change in voltage. So if I wanted to convert this voltage graph to a charge graph, I just multiply by multiply by C. So Q across the capacitor is delta V times C. So it's going to have the same look as a voltage graph. It's just going to be scaled by C. So it'll look identical to this, except for instead of being delta VC up here, it'll be Q up here. And instead of being E, it'll be E times the capacitance. Yep. Other than that, it'll look identical. So it's just a scaled version of the same graph. For discharging, it is more like an archetypal graph. So discharging, here's my Q, say. I start out with some Q naught, and it will discharge down to 0 with the same time constant. So that's what discharge looked like. I thought the graph for charging the capacitor was negative. Yeah, oh, I remember this. So there's a bit of confusion because, yeah, in one of the lecture videos, I think I chose a sign convention which was like slightly different than usual. So what I'll say two things. The first thing I'll say is ultimately these sign conventions aren't going to be a big deal. But the other thing I'll say is that usually when you think of charging a capacitor, usually the way that we think of charging a capacitor is starting at 0 and then going up to some positive value, the battery voltage. So when I do that, let's look at this. I will show, here's my system. It's a capacitor. Here's a battery, and here's a resistor. So when I find the change in voltage across my capacitor, the change in voltage across my capacitor as measured from the direction of the current flow, so like if current's flowing this way, will be a negative number. Delta VC will be negative. But practically speaking, we're usually interested in the magnitude of this thing because eventually we're going to discharge it. So usually we write it as going up. If you wanted to write the change in voltage as like final minus initial going with the current as opposed to away from the current, then it would, yes, it would be negative like this, going to some negative value, the same negative value that it would up top. So it's kind of just a choice of sign convention. What I'll say is that like I'm not going to penalize you if this kind of thing comes up and you draw it negative. I'm not going to have a problem with it. Yep. Because it's really just your choice of like whether you want to think about 2 minus 1 as being with current or in the opposite direction of current. Is that okay? Is that all right? Feeling okay about that? Okay. All right. I think that's most of what I wanted to say for charging and discharging capacitor. There are formula that describe each of these. They're provided on the sheet. Yeah, it's pretty much again though just this or no, I shouldn't say they describe each of them. We do the charging only, but the general case is like we have a constant, we decay to it. So in general, a decay looks like x equilibrium, the final value, plus x naught e to the negative lambda t, something like that. Double check myself. So as we go to infinity, this will be 0, we'll be left with equilibrium. Yep. When we start at time t equals 0, it's not going to be x0, it'll be x equilibrium. I say delta x initial, whatever. So the point is I start some height above my decay point. So here's my delta x initial, and I'll decay to that. But the concept is identical, and we won't ask you to do calculations involving like non-zero or non-battery voltage decays. Yeah. Is the delta V in the equation magnitude then? That's right. Yes, I would. This is typically magnitude. Yep. Yeah.
So the x of t equals x equilibrium plus delta x. That's just if we were having a discharge.
So this is, yeah, so this would be like if we're charging up to some higher value, that higher value would be my equilibrium point. If I'm discharging to a value that isn't 0, like so say I'm discharging and there's something that's kind of, I don't know if I want to get into the weeds too much on this, but it's possible to have capacitors that don't decay to 0 voltage, but instead decay to just like some finite voltage when they discharge. That would be our equilibrium point. So the equilibrium thing is just the thing that we decay to, the value that we decay to. Yeah, sure thing. Does the current flowing through a capacitor decrease as it charges? Yes. Yep. Yes, that's true. So I can tell that if you like from the derivative of my Q graph, but another way to think of it is just that like as the capacitor charges up, it's got less and less room in the end, so to speak, less and less space for more charges to flow into it. So all of the charges that are already into the capacitor are kind of trying to push the charges that are trying to enter away, and that slows down their current. So are we only going to be dealing with capacitors charging to the battery voltage, discharging from the battery voltage? So that's the question. Sorry, I should probably speak a little more clearly. Are we only going to be dealing with capacitors charging to the battery voltage / discharging from the battery voltage? I'll only ask for computational expressions involving like, so at a specific time, say, oops, hello, wrong place. At a specific time, say, all right, there we go. I'll only ask for you to deal with the equations directly for charging to and from the battery voltage. Yep, that's right. I won't ask for you to say like, I'm between these 2 points. X equilibrium is 15. Our initial voltage is 500. What is it at time equals 4? Nothing quite like that, no. The only circumstance where that'll be all right is if it's to or from the battery voltage. Okay, I think I probably want to move here. Are there any wrap-up questions about exponential decay in the context of circuits? And I'll talk about it briefly over here for the fluid system. Can you go over a capacitor in parallel and max VC in this case? Ah, okay, interesting. Yeah, sure. So yeah, that's cool. Let's do that. So in parallel, I assume with a resistor, or let me just draw something. So here's what I'm imagining. Something like that. Is that what you're thinking of or something else? Okay, cool. So, oh, and let me add one more thing to it. I'll add this other resistor. Okay, so what I'd say about this is, again, I don't like this is a little bit more maybe meaner than we would usually go, but I can talk about it for a second. So the maximum voltage across this capacitor is the subject of interest. We're wondering what that might be. And what I'll say about it is, at the end of charging, the capacitor will not accept any more charges and current through the upper branch will be 0. So when it's fully charged, there will be no current through the upper branch, which means that all of the current is going to flow around here. So the change in voltage across this capacitor is going to correspond to the change in voltage across this resistor, delta VR. So the change in voltage across the capacitor is going to be the same as the change in voltage across this second resistor. The way that I would find that explicitly is by knowing the equivalent resistance of these two resistors. So Req, again, so when current through the upper branch is 0, this branch might as well not even exist as far as the rest of the circuit is concerned. So the equivalent resistance of these two can just be added directly. There's no leaks, so to speak, no upward leaks at that point. So the equivalent resistance would just be R1 plus R2. That'll tell me the R1, R2. That'll tell me the current through this loop, I. And from that, I can determine the voltage drop across this resistor. So that's how I do that really quickly. And I know that was probably a really quick overview, but after a long time, the change in voltage across this resistor will be the same as the change in voltage across the capacitor. So this middle resistor, the one it's in parallel with, those two things will always be the same. But after a long time in particular, that voltage across that resistor will be the same as the voltage across the capacitor. And we can find how much current is flowing through it by basically analyzing it like we would just a 2-resistor circuit. Benjamin asks, in this case, RC would just be R1 times capacitance. RC is in tau. So I think, yes, it would be very close to that. Yes, I think I'm pretty darn sure that's exactly what it is. Yes, the answer is also don't worry about it. Yeah, that's an acceptable answer. Good. So the answer is also don't worry about it. That's fine. Yeah, you won't be dealing with anything. Again, no, we won't have capacitors in parallel with, directly in parallel with other resistors with no battery involved. Yeah. However, I do think R1 times C would be our tau here. That's right. Question, go for it.
I did have a quick question. So I've encountered problems where like there's a switch and
Yeah.
it was asking about like immediately after the switch is closed, what would be
Yeah,
like
sure.
what would happen? Could you explain that? Because now I understand it at max charge, but what about when it's like right at the beginning?
So when we say right after we close the switch, usually that means that I'm changing my circuit in some way. So for example, I don't know, where should I put the switch? I'll put the switch here. So maybe I charge up my circuit, and then at some time after I've charged it up, I hit this switch and I say, okay, what happens when I close the switch? And it's like, okay, well now current is going to flow through this resistor. So the capacitors are either going to charge or discharge to reflect that. And in particular, this capacitor would discharge because this one's got, like, this is essentially setting the voltage difference at some number that is less than the battery voltage. So the capacitor would have to like discharge a bit to do that. Yeah, so when I hit a switch, usually what I'm doing is I'm either saying, okay, I'm transitioning from capacitor charging to capacitor discharging, or vice versa, capacitor charging to capacitor discharging. Usually that's what happens when I hit a switch. Sometimes when I hit a switch, what I do is I short the circuit, but that ends up still just reducing to, is my capacitor charging or my capacitor discharging? Is that okay? I know it's a little bit vague.
Yeah, I think that makes sense. If you had maybe put the switch like where you have like written I equals 0.
Yeah, sure.
And so then you had closed it there. How would the current be splitting between those two
Oh, sure.
parallel.
So, okay, good. So at time t equals 0, if the capacitor is uncharged and I close the switch, the current will all flow through up here. So an uncharged capacitor acts as a wire, or I say it's resistanceless. An uncharged, there should be a G there. Uncharged capacitor acts as a wire, it's resistanceless. A fully charged capacitor carries no current. Carries no current. Or if you like, you can say it's like fully resistive. I hesitate to say it has infinite resistance because really what you're talking about is like the, it's kind of a game between both the capacitor's voltage and the whatever's supplying the capacitor with voltage. So it's not really infinite resistance, but it is true that a fully charged capacitor carries no current. There'll be no current going through it. Does that help? Is that all right? So
Yeah, that's exactly what I needed help on.
Yeah, good stuff. Sure thing. Okay, we should move off of here. We got 45 minutes left. We got a lot of ground to cover. Is that cool with everybody?
I just one last real quick question. Is delta VR the R equivalent or just that one little resistor?
So in this context, I mean this resistor. So it's the resistor that the capacitor is in parallel with. Again, though, we don't plan to ask we don't plan to ask questions about capacitors that are in parallel with only a resistor like this. Yeah, it's a bit next level. Okay.
Thank you.
Sure. All right. So last thing, fluid systems. Same deal. Still exponential decay. The thing that decays is the distance between them, or the how do you say the difference in the heights of their two surfaces. Here are the time constants, time constant and lambda. One's just an inverse of another. Okay, and we can transition smoothly from half-life to tau to whatever we want with the appropriate like multiplication by natural log 2. And that's again just on the formula sheet, but I'll write it here so we have it. So tau is 1 over lambda, which is a half-life divided by natural log 2. Boom. So if I have any of these, I can convert to any of the others.
Hey, Adam.
Yeah.
I have a question for that fluid system on the left right there, that in red.
Yeah.
So when these two tubes are going to reach equilibrium, will the heights in both of them be equal? Like,
so the absolute heights above the ground, say, will be equal. Yes. So the absolute heights will be equal. So the flat earthers will tell you that water always finds its level. So the absolute height above, say, the surface of the earth will be the same. However, sometimes we ask problems where there's like two pipes that are on a slant. So something like this. So the relative heights, like from the bottom of each of them individually, will not necessarily be level at the end, like will not be the same number, but their absolute heights will be same. Yeah, the equilibrium absolute height relative to the ground is the same at the end.
okay.
Does that help?
Yeah.
Nice. Thanks for the question. Okay, in one exponential decay DL that we talked about heat flow, do we need to know that for the final? Nah. Heat flow is cool, but we didn't explore it deeply enough for it to be like really interesting. We can't ask you to expand on it. Thanks, V. Okay, what else? All right, I think that's really all the time I want to spend on exponential decay, even though it was one of our favorites. Let's keep moving, or favorites, one of the ones we favorited. Vectors, for something completely different. Let's zoom in for these vectors. Let's go. So here's vectors. Vectors are fundamental to the second half of the course where we talk about forces and momentum and all these other things. So the two, four. Okay, four concepts. Four concepts to get from vectors. The first concept is that a vector is basically just a number, but now in like more than one axis. So a vector, I'll call it A, consists of several components. In here we do just 2D, but all of this generalizes really nicely to more dimensions too. but it's just 2 components. And on an xy axis, I can draw my vector in as ax, ay. Here it is. It's a vector that points like that. Oh, hello, phone. All right, so there's my vector. It has magnitude and direction. If I'm given the magnitude form of it, so if I have the magnitude of it, then I can calculate, and an angle measured relative to the x-axis. Then I can calculate the x and y components by magnitude times cosine theta. And wait, double check myself there. Yep. And a y is magnitude times sine of theta. This is called vector decomposition. It lets me decompose my vector from magnitude and direction form into components, x and y. So this version up here, I call the component form. Whoa, looks like we got a couple. One question is, but not all the time right. Sorry, I'm not sure what that's referencing. I kind of left it over. Okay, sometimes ax can be sine. That's right. Yeah, so if I were to measure my angle relative to another axis, so if I measured it relative to the vertical axis, then it would be switched. So ax would be a sine theta, and a y would be a cosine theta. Typically, things are measured relative to the positive x-axis. So if you just kind of write down a default formula, the angle is going to be measured relative to the positive axis. Yeah, when talking about vectors. But yes, that's right. So when in doubt, rely on trig. So when in doubt, remember that this is really just a triangle. The y component is on the opposite, and the x component is on the adjacent. So, and that'll tell you how to get from one to the next using your hypotenuse A. So SOHCAHTOA. And I include SOHCAHTOA on the formula sheet as well. So if you don't feel like you have to memorize it if you aren't coming in with like mega trig skills. Then you go into a situation where we don't use sine for y comp and don't use cosine for x comp. That's right. So basically, anytime I measure relative to a vertical axis, they switch. Yep. Anytime I measure relative to a vertical axis, they switch. Is that okay? Or still a bit weird? Okay, I'm gonna let that one sit for a while. Next thing I wanted to talk about, so we've introduced the notion of a vector, we've introduced what it means to decompose a vector. The next thing I wanted to talk about is multiplication by a scalar. So if I have a vector, so let's say I'm doing, just to jump ahead for a moment, let's say I'm doing angular momentum, L, and I'm multiplying the moment of inertia times the angular momentum, or the angular velocity, sorry. So if I know that the angular velocity is like 3, 0, and I know that I is 15 of whatever units, I think it'd be kilogram meter squared. Then when I multiply these things together, what I do is I just apply the scalar to each. So it'd be like I times omega in the x direction, comma I times omega in the y direction. So I just multiply each component by the scalar. That's multiplication by a scalar. To write that in terms of like mathy notation, if I say C times A, where A is a vector and C is a scalar, that's just C times AX, comma C times AY. Each component gets scaled by the scalar. Cool. Last thing, addition of vectors. So if I have 2 vectors A and B, so maybe I'm now adding together 2 different moments of inertia, not moments of inertia, sorry. I'm adding together 2 different angular momenta. Then I just add their components. So the first part of each vector and the second part of each vector get added. That should be a BY, sorry. So that's vector addition. You do multiplication before addition. There's a, what do you call it? Is it PEMDAS? Yeah, PEMDAS for order of operations for for vectors too. Multiplication happens first before addition. Will we be asked to find the I of objects, as in the moment of inertia? So short answer for this one is, if we ask you to find the moment of inertia of an object, it'll be for like point bodies only. So like maybe I could theoretically have like an origin, and I say, here's a couple of R's for this body, and here's 3 different masses, R, R1, R2, R3, and here's mass 1, mass 2, mass 3. That's something we could theoretically ask you for. We won't ask you to find it for any kind of complicated geometry like a sphere or a cube or anything like this, no. Okay, but so for vectors, that's pretty much all I really want to say. Vectors, I think we've had to work with them a lot, so they're probably getting comfortable, but these are the fundamental rules of them. There's the component description, there's the magnitude and direction description, and there's addition and multiplication of vectors. Any wrap-up questions on vectors? Otherwise, I'll hop on to the next thing. Okay, so Austin asks, for the example I gave, is it I equals 3m 3r squared? So in general, no. If the masses and velocities, or the masses and r's are different, then I'll have different, it'll be different. So the moment of inertia is defined as the sum of mass I times ri squared. But we'll get here in a minute. That's not quite a vector thing. But so it'd be a sum of different ones. No worries. Thanks for the question. Okay, linear momentum and force. Who's hanging with me here? Let's get claps if you're like, I'm trying to go to sleep, and thumbs up if you're like, I'm all right, and thumbs down if you're like, get me off the ride. Cool. Okay, we got thumbs, we got claps. I see you. We got the cries, we got ta-das. Let's go. Okay. Let me run down now to linear momentum and force. So linear momentum and force was the first place that we actually applied these vector concepts. Linear momentum and force was the first place we applied the vector concepts. So linear momentum, first of all, the reason we care about it, what is it and the reason we care about it? So linear momentum is a vector quantity. Linear momentum is a vector, P for some mass M. And what it describes is the velocity of that object scaled by mass. Roughly, the way I think about momentum is it tells me how difficult it is to change the velocity of an object. So yeah, so if something has a lot of momentum, it's hard for me to change its momentum. If a car is coming at me at 50 miles an hour versus a fly coming at me at 50 miles an hour, I know which one's momentum or which one's velocity is easy for me to change. So boom. This is the definition of momentum for a point. Now, because momentum is a vector, it can be added just like any other vector. So if I have a system, momentum of a system is the sum of the momenta of the individual components of that system. So if I have like 12 objects and they're all flying around at some different velocities with different masses, I can just sum up their individual momenta to find the total momentum. Saeed asks, momentum and inertia, are momentum and inertia analogous? Kind of. So yes, they're analogous in the sense that like mass, typically we think of mass as being a stand-in for inertia. So mass is a big part. Mass is the thing that is constant as something's velocity changes typically. So yes, that's my intuition for it, is that it's more, usually I think of it as being more to do with inertia, because like velocity freely just varies. But when in doubt, if your intuition starts to fail you with that, always come back to the definition. It's about the math. So yeah. Sorry, I know that's probably not the most like compelling response, but inertia is part of it, and the other part's velocity. Okay. I had a thing I was going, okay, the reason we care about momentum, so the reason we care about it is that the total momentum of the universe is conserved, which is to say that like the momentum, as elements of a system exchange momentum with one another through like collisions or like forces or whatever, as they exchange momentums around, the total momentum of the entire universe is conserved. The way that we say that is that if there are no external forces, if there's nothing outside my system messing around with me, then the change in momentum of my system is 0. This is what conservation of momentum is for a system which is free from external forces. So anytime we have these momentum type problems, it's important to carefully define what your system and what your rest of universe is. So if I throw a ball, it may be useful for me to consider my hand and the ball as my system. Or it may be useful to just consider the ball as my system. And I just need to be really explicit about that whenever I start the problem. Usually you know based on what the question asks. So if the question only asks about the ball, good shot that the hand doesn't really matter. Okay, there's a little bit on momentum, a couple other things. So the way that momentum changes is through force. So force is the mediator of change in momentum. Force is not a thing that's required to maintain a velocity. Force is not a thing that's required to maintain a velocity. Instead, force is the thing that changes a velocity. So the impulse, J, is force times delta t. Whoa, force times delta t. Now, I can think about this as the force as being a force that's acting on an entire system, in which case J refers to the change in momentum of my entire system. Or if I think about it on a particle-particle basis, like an element of my system to another element of my system basis, the force can just mean the force between two elements, say, can tell me about the change in momenta of each of my two elements. So this is a very general equation. I can use it on the system scale. I can use it when I'm thinking about the whole system, and I can also use it when I'm thinking about individual elements in a system. Okay, so force times delta t gives me changes in momentum. That's the key takeaway. Force times change in time gives me changes in momentum. Typically, the mass of our system doesn't change. So usually I can write F times delta t is m delta v. When the mass changed, this equation breaks. So I'm not going to box it, but this is how I usually think of it. Forces cause changes in velocity. Forces cause changes in velocity. Okay, so there's linear momentum. Quick questions here, I'm gonna have to pick up the pace. There's a question, what's the difference between ang j and j? Ang j refers to the angular version of this linear j. So ang j is going to refer to the change in angular momentum, whereas j, the impulse, refers to the change in linear momentum. So angular momentum means rotation, usually around your center of mass. Linear momentum, or impulse, refers to change in your linear momentum or your velocity, like relative to the rest of the world, the velocity relative to your coordinate system. So to put it another way, it's the difference between this section and this section. Okay, so angular momentum, we carry over some of the same intuitions. So angular momentum, to touch on it briefly, we're getting a little bit closer to things we've been working on recently now. Angular momentum is L, which is I, the moment of inertia, times omega for some body. So if I've got a body that's rotating, omega tells me two things. Omega tells me both how quickly it's rotating, and it also tells me the direction, an axis about which it rotates. So omega, if it's a large number, say it's like 500, tells me that it goes 500 radians per second. It travels 500 radians per second as it rotates. I, the moment of inertia, I is the sum mi ri squared this tells me basically if I discretize, I don't know, that's a big word. So if I chunk up my object into a bunch of little chunks of mass and measure out a bunch of different distances, a bunch of different r's to each of those chunks of mass, and sum up all of those chunks of mass times the vectors that lead to them squared, the magnitude of those vectors squared, and I sum up all of those individual contributions, that gives me the moment of inertia of an object. We won't ask you to do it for anything complicated. We may ask you to do it for like a single mass or two masses, say. So there was a question earlier, which was, what would the moment of inertia be for this system, where I've got three masses, m1, m2, m3, and three associated distance vectors, r1, r2, and r3. So the moment of inertia for this system would be I equals m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Yuck. But I could do it if I wanted to. Was there a question there that I missed? And I probably should stay here in case anyone was taking notes. If m was same and r was same, could we make it 3m 3r squared? So no, in that case, if m and r were the same, it would be like these would all be the same. So like the m's would all just be m's, the r's would just be r's with no subscripts. So it'd be 3m r squared if they were all the same. So the sum is the most important part, not the multiplication.
Why in this case are we adding moments of inertia?
So each point in my system contributes an mi/ri squared. So the individual moments of inertia of each point are mi/ri squared, and yeah, and when they're points, they sum nicely like this. If it's like a continuous thing, if it's like a disk where like it's not a single point, but it's like different little lumps, or it's a continuous body that it's not localized around a single point, then it gets a little bit more complicated. But individual points, their moments of inertia do add. Individual points rotating around an axis, their moments of inertia do add. Is that okay, or is that still a little wonky?
So is that just like are we talking about one, like something with a general like direction of movement in that like upper right hand direction?
So in terms of what this represents, this I, the I represents the moment of inertia of these points if they were to rotate around this point, the pivot point here. So so it tells me how hard it would be to cause all of these things to rotate in like a circular direction around this point. Is that kind of getting more to what the question is?
Yeah, so like if there was just, because we've seen like examples where it's like a ball on a string, that would be in this case 3 separate balls on 3 separate strings. Is that
right? That's exactly right. Yep, it'd be like three yo-yos instead of one yo-yo.
Okay, thank you.
Good stuff. Thanks for the question. Natasha asks, if we move the pivot point to one of the masses, how would that change I? So if I rotate it around one pivot point, around one of the masses instead, overall it's going to decrease my I as my guess, but I don't actually know that for sure. So now I have these R's instead, and so I redo my calculation. The I around this new pivot point would be R2 M2, sorry, and the R would be squared, plus M3 R3 squared, where this is my R3, this is my R2. And then this point wouldn't contribute because R there is just 0. Yeah, so the axis you rotate around does matter as well. Thanks, Natasha. Okay, we really should move. Sorry to cut it off there, but we should move on to. Oh wait, no, actually, we're still on angular momentum and torque. So there's our I. Let's head over to torque, just briefly, to chat about the last two. Okay, torque. So what's torque? Torque is like force. So in the same way that for linear momentum, force acted over time to change our linear momentum, torque causes changes in our angular momentum. So torque times delta T is delta L, which is ang j? Someone asked about ang j. So ang j is the change in angular momentum of a system under torque. Now, torque is, it has this nice analogy to force, but it's not quite as simple to conceptualize. So the definition of torque for a system pivoting around some pivot point, or for a system that is, pivoting around some pivot point where I've got a force being applied some distance away from that pivot point, r, some displacement away from that pivot point, r, where there's a force being applied, F. The torque is given by r times F times the sine of the angle. So magnitude r times magnitude F times the sine of theta. So that tells me the magnitude of my torque. The angle, that theta, is measured between r and F. There's my theta. Alternatively, and I don't want to. Yeah, question.
Sorry, wouldn't theta be on the other side of that because that's where the head and tail meet?
So you can choose theta like this. That's fine too. So either will end up giving you the right answer. If you mean, do you mean this one, theta that way?
The one you had before was what I meant.
Yeah, this one.
Yeah.
So they'll be equivalent, and this is because so it's because sine is symmetrical, but it'll end up being the same answer either way. Yep. So either way you like to measure it, whether you like to measure it relative to the extended line from R, or just between the two, like the shortest distance between them, either way will yield for you the same numerical value. And to kind of motivate that a tiny bit, it's because sine looks like this. So we're kind of like on opposite sides of a hump here. So we're referring to either the smaller theta, which is like the black point, or the larger theta, which is like this point. So they give me the same value out. They spit out the same value. Yeah. So the way we say that with like math words is that like sine is symmetric about pi over 2. Yeah, sine is symmetric about pi over 2. Another question for calculating torques: when will we use cosine or sine for the R or F perpendicular? So if you're measuring the angle, so if you're measuring the angle like this, like from R to F, then it'll always be sine. I'm trying to think of any times when you would use cosine. Yeah, I want to say it'll always be, like if you've got it drawn out like this, and you've got this theta here between them, it should always be sine. When would I ever use cosine? Yeah, I can imagine that maybe possibly you don't have it in a form like this, and so then you might need to use some trig. So I'd say if you encounter some kind of weird torque situation where you don't have this angle well known, then fall back on your trig. So I draw in my R, I draw in some F that points out some direction. F, maybe I know something about the length of these two vectors or something, and I need to find this angle, and maybe I need to use cosine then. But I'd say overall, if you've got it in a form where you know the angle between R and F, it should always be sine. Yeah. If you have a different angle that's not that angle, you might have to do some creative angle movement.
Hey, Adam.
Question.
I have a quick question. So for the torque equals RF sine theta.
Yeah, this guy.
Basically using that equation when you have a force that's not perpendicular to your R, so you need to find the perpendicular force.
That's right. Yep, that's exactly right. So if they're perfectly perpendicular, then my angle is just 90, and it reduces to just RF. Yep. But if they're not perfectly perpendicular, then your theta comes into play. It alters the torque. It'll always make it smaller. So if my angle is not 90 degrees, then torque will only be a smaller number.
Okay, because you're finding like basically the component instead of like.
That's right, because you're only finding the component that points perpendicular to R, or the component that points perpendicular to the other, whether you're finding F perpendicular or R perpendicular. Yep, good question. That's right, sine 90 equals 1. Hopefully I said that, I don't remember. I might have said something wrong. Okay, got about 15 minutes left. These have all been really good questions, thanks, but I probably should make moves now. We've got angular momentum and torque. I feel like that's fairly well covered. Torque causes changes in angular momentum. Angular momentum is a measure of the distributedness and massiness of the object. So the angular inertia or moment of inertia, and the rotation rate. So that omega, how quickly it's rotating around an axis. And torque affects change on the angular momentum over time. So torque times delta t gives me my delta L, my change in angular momentum. Okay, next part, static equilibrium. So static equilibrium is very small, so we'll take 5 minutes or less. I'm going to put a hard stop there so we can at least hit the kinematic equations. So static equilibrium, because I know it's got a star. Static equilibrium basically tells me two things. If we've got a system in static equilibrium means, hello Zyboard, help me out. Static equilibrium, the static means velocity equals 0. Velocity equals 0. It also means that the angular velocity is 0. Equilibrium means that forces are 0. So the sum of forces are 0 and the sum of torques are 0. The way I like to think of this in words is that static equilibrium means it's not going anywhere and it's not going to be going anywhere, right? So the velocity being 0 and angular, I think I might have said angular momentum a second ago, but angular velocity being 0, that means it's not rotating and it's not moving, like it's not translating left to right. The sum of forces being 0 and the torque summing to 0 means it's not accelerating. It's not accelerating left to right, and it's not accelerating in a rotational direction. So it's not going to be going anywhere either. Static equilibrium means it's stuck in place and it's not going to be moving later. So these are my two conditions. The conditions for static equilibrium that are usually most interesting mathematically are these ones. The sum of forces needing to sum of 0 and the sum of torques summing to 0. Our archetypal example for this is a seesaw. So I've got a seesaw. We're stuck. The kiddos are stuck on the seesaw. They're each some distance away from the pivot point. Let's put a tier on. Oh, I'm not going to put tiers. All right, fine. So there's some distance away from the pivot point, R and R2, R1, R2. If this is to be in static equilibrium, I need for the forces exerted by the kids to be canceled. So F2, F1. I need those to cancel with something else on the system, namely usually the hinge force. So some force by the hinge that cancels those two, F hinge. And in order for the system to stay in static equilibrium with no one moving, I need the torques to cancel. So that means that if there's a torque, say this kid is producing a torque that is into the page, and this kid is producing a torque that's out of the page, I need for all the torques of my system to sum to 0 as well. So that's static equilibrium in a nutshell. So I'll say torque 2, torque 1. Now is a good time for a quick refresher on the right-hand rule. So the right-hand rule, you need to use your right hand. So every time we give the final live, I look around and every once in a while I see somebody stick out their left and I'm like, oh no. So you want to use your right. Make sure you're using your right. If you don't know which one's your right and left, learn a trick, right? So for me, if I stick out my left hand, this is my left. If I stick them out with my palm facing away from me, this is my left. So right hand rule, that's what I want to use. What I do is I take the palm of my hand, I orient my palm so that it sticks near the pivot point, and then I rotate my fingers in the direction of the force. That's how I would find the torque. Or if I'm using angular velocity, I stick my finger, my palm at the center, and I rotate my fingers in the direction of the angular velocity, and that gets me the direction of the angular momentum. So here, for example, for person 2, so follow along if you like. For person 2, I take my hand, I'm going to do it from your perspective. I stick it at the pivot point, which is on the at the triangle part of the what do you call this thing? The triangle part of the seesaw. Then what I do is I take my thumb, I move my hand around so that I can move my fingers in the direction of the force. So the force is pointing down. So I move my fingers in the direction of the force, stick out my thumb. That tells me the direction of the torque, yeah, which is in this case out of the page. A couple of questions coming in. When is there a non-zero pivot force versus a 0 one? So okay, so I can give kind of like a flippant response. Here's the mean one. So there will be a non-zero pivot force when the sum of all of the other forces is non-zero. So when there still needs to be some forces canceled, that's where the non-zero pivot force comes in. So there's a 0 pivot force when all other forces cancel. Yeah, it's not that. Actually, that's not a terrible response. Is that okay? Hopefully that's all right. Okay. Yeah, sure thing. Thanks for the question. And Jordan asks, palm is always on the pivot. Yes. Yeah, your palm should stay on the pivot throughout. Yeah. So like if I were to move my palm over here, say, and then now I'm suddenly pointing the wrong direction. Oops, pointing the wrong direction. So your palm should pretty much stay on the pivot, but it's free to pivot around the pivot, haha. So it's allowed to go like this as you try to find an orientation where you can stick your fingers in the direction of the force. Yeah, sure thing, Jordan. Okay, isn't it in? So when I do it with my right hand, I get out of the page. Yeah, I get it coming toward me. So I draw my dot. Okay, it's been 5 minutes, so I'll call it there for static equilibrium. That's all static equilibrium is. The sums of the forces have to sum to 0. The sums of torques have to be 0. The last things to talk about are Newton's laws and the kinematic equations, which I have spelled correctly. Let's go. All right, and I'll make those go right here just for fun. So the kinematic equations, well, we'll do the kinematic equations. I'll say Newton's laws just that we have them in our head, but we've seen them all before. So Newton's law says, Newton's laws, there's 3 of them. Newton's law says that delta P is 0 if there's no F external. Or another way to say that, equivalent is delta V equals 0 when F equals 0 for a point object. So there's no change in the velocity when there's no force. Velocity is constant over time. That's number 1. The way we kind of like have codified that is to say that an object in motion stays in motion unless acted upon by an outside force. So when force is 0, there's no change in velocity over time. The second law specifies how velocity does change. So it tells us that force is mass times acceleration. The force is the mass times the acceleration. Or the way that we've seen that in the context of momentum is that the change in momentum is force times delta T. That's equivalent. So these are equivalent statements. F equals ma is the more Newtonian way to think of it. The last one is that forces come in pairs. Forces come in pairs. For every action, there's an equal and opposite reaction. So if I've got 2 bodies that are interacting with one another, say big body and little body, the force, I'll call this one 2, and I'll call this one 1. The force of 1 on 2, or of 2 on 1, sorry, of 2 on 1 is equal in magnitude. Let's make sure those are equal sizes. Are equal in magnitude to the force of 1 on 2 and opposite in direction. So force 1, 2 equals negative force 2, 1. That's the way that I codify Newton's third law. Forces come in pairs. There's Newton's laws. I've got a question from Natalie. Asks, if we know the force is going clockwise, can we just assume it's into the page? Yes, that's equivalent. Yep, that's fine. So if you're more comfortable thinking about it as clockwise versus counterclockwise around a pivot point, that's okay. It's identical. Yep. So if the force is going clockwise or is pushing it in a clockwise direction, that is an into the page torque. If I've got a torque that's trying to push me counterclockwise, that's an out of the page torque. That's identical. Yep. Same as the right hand rule. And there's nothing particularly mystical about the right hand rule. It's just, I think Patrick said it's just a sign convention, which is true. It's just a sign convention. If we wanted to go with the left hand rule, we could, but a lot of our other coordinate systems would be kind of different and uglier, I say. Okay, what else? All right, that's it for Newton's laws. Now, I want to take a couple minutes to talk about the kinematic equations. We'll probably go to time on this. I can stay for maybe 5 minutes over. Let's hit kinematics. So the 4 kinematic equations, what I'm going to do is I'm just going to actually pull them over from my lecture because they're annoying to write and my handwriting's bad. So 1 second. Snip. Where are you? Hello, Snip. There you are. Okay, so these are my 4 kinematic equations, which are just statements about the way that a mass acts under the influence of constant acceleration. So, which is the same as constant force. So these tell me how a mass acts, a point mass, a single massive body acts under the influence of a constant force, aka constant acceleration. Okay, there we go. Hello. All right, there we go. So what do each of these things say? The one that I think is easiest to talk about is velocity, but that's also because I like calculus, so it might not be the easiest for everybody, but I'll say it anyway, which is this third one. So the third one just tells me how velocity changes for an object under constant acceleration. I multiply my acceleration by some change in time. That tells me how much my velocity has changed. Intuitively, the way I might think about this is, or semi-intuitively, using some vectors for intuition. Oops. Hopefully I'm caught back up, Austin. Okay, so intuitively, the way that I think about velocity is if I've got some initial velocity, vi, and I've got some acceleration, the acceleration scaled by delta t gives me, if I add those two vectors together, that'll give me the final velocity, vf. So acceleration acts through time to kind of add or subtract off from our initial velocity. It just kind of throws a little bit more on there or takes a little bit off. So yeah, so that's how this first equation works, is I start with some initial velocity, say, I've got some acceleration, I dial time forward, that changes my velocity, and that change is just linear. It's not ax times xt squared or delta t squared or anything like that. Now the subscripts are kind of important to think about for all of these equations. So if I have a vx, that's telling me I'm using the component of velocity that points in the direction of the coordinate. So like here, my velocity is pointing in this direction. So I've chosen to use the component of acceleration that points in that direction. Acceleration overall doesn't have to point in that direction. So for example, if I've got a velocity that points like this, and I've got, say this is just an object that is under the influence of gravity. So velocity and the acceleration is just some vector that now points down, a g, acceleration due to gravity. The only component of velocity that's going to change is the y component. So over time, here's vx, here's vy. The only component of velocity that changes is the x component. So if I dial time forward a little bit, starting to lose my voice, here we go. Pretty good, almost right on time. If I dial time forward a little bit, my velocity will not change in its x component, but only in its y component. I've got a change in velocity. So here's my, I'll write this in orange. Here's my change in velocity, which is just ax, or AY, I'll say A in the direction of gravity times delta t. That's the direction in which my velocity was influenced, only along its y component. The x component stayed the same, bx. Kate asks, will we have to use kinematic equations for objects that have x, y components, or are we just analyzing 1D movement? Generally, it's possible that we could ask you to do 2D. Practically speaking, it's identical. I mean, it's the same as 1D. So, yeah. So, how do I say that a different way? The kinematic equations only apply individually in one dimension. So, yeah. So if you do have to use them in 2D, it'll be like doing the same sorts of operations twice. You'll need to find your acceleration in each direction. You'll need to find your velocities in each direction, and then add or subtract accordingly. Hopefully that helps a little bit. I'm not sure, but so these are component-wise equations. So if I have like multiple different components of my velocity, then you apply whatever equation you need to apply multiple times. So it's like double the work, true, but it's the same kind of work. Sally asks, can we use kinematics to find every point needed to graph velocity and acceleration graphs? Yes, essentially yes. So the kinematic equations are especially good for telling you how to go from acceleration to position. You can do the reverse, but it's usually a little bit hairy. So usually kinematics are good for getting you from acceleration, say, to velocity and position. However, it is like technically possible to go the other way as well. But it is, like I said, it's kind of hairy. Like if you try to invert this for delta t, if you try to get delta t out of that equation, yeah, it's just more annoying. Yeah, but like, for example, solving for acceleration directly from here is actually not that bad, right? If I have all the initial conditions and I know delta t and I know x final, I can find the acceleration. It's just going to be x final minus x initial minus this term times 2 over delta t squared. So yeah, the advice that I give is to, if you're confronted with a kinematics problem, make note of what variables you have. So like I'd say almost like literally make a list of like, here's what I have. I know my initial position, I know my final position, and I know A, and I know delta t. Okay, so they're asking me for velocity, but I'm missing final velocity. That's fine, I don't need final velocity. So you kind of have to suit the problem to how do you say this? Suit the equation to the problem based on what you know and based on what you don't need, what you don't know. So a lot of times, I think the most common one that's like it's hardest to figure out when you need it is when you've got everything except delta t. So the example that I've used previously is like, say I'm dropping a water balloon off the top of Rossler Hall, which is not at all skyscraper shaped, but whatever. I'm dropping it off the top of Rossler Hall, and it's falling down to the ground, and I want to know what's the final velocity right before it hits the ground, Vf. Well, I know the height difference, say, but I don't necessarily know the time difference. So if I don't know the time difference, boom, this equation is probably going to be a good one for me. Maybe I've got all of the initial and final conditions, or so I've got 2 of the initial conditions, say, and 1 of the final conditions, and I have the change in time, but I'm looking for the other final condition. I'm missing A. This equation would be a good one for me, and so on. So it's easiest to think about the kinematic equations in terms of what they're missing. Yeah, what they're missing. But I'd say if you encounter a kinematics problem and you're not sure which of these to use, literally make a list of the variables you know, the variables you have values for, and see which ones you can and can't use. If you have enough information, you may be able to use multiple of them. You may be able to use like whichever one's simpler of 2 or 3 of them. As I tried to show in my lecture video, they're all derivable from one another. So like it's usually just a question of like finding the simplest way to do it, not the not finding like the only possible way to do it. Okay, I know I was kind of like rambling there for a moment. The last thing I want to talk about in line with our last lecture is these acceleration, velocity, and position graphs, which, by the way, I made an error in one of my computations toward the very end of the position graph in that lecture. So if you noticed, I think somebody who's probably here brought that up to me, but if you're kind of scratching your heads about one of the computation at the end, check out the errata for that video in the comments, or not the comments, the description. It was a minor thing, but it looks really funky. So yeah, I made a sign error. Okay, so say I've got some chunk of constant acceleration over time, some chunks. So what the kinematic equations are good for telling me is how velocity and position will change as a result of this. And this will be my last example. We'll stop right around here. So say this is 1 and this is 4. The acceleration graph tells me the slope of the velocity graph at any point. So it tells me that from this initial time to this final time, I'm going to have a slope of 1. It doesn't necessarily tell me about the initial positions or anything like that, but it tells me about the change in velocity. The initial velocity or anything like that, but it tells me about the change. In this second interval, the slope is 4, positive 4. So it'll be really steep up like this. Steeper than I've drawn it even, but I wanted to save space. From that velocity graph, I can determine things about the x graph. So the velocity graph alone doesn't tell me anything about the initial position of x, but let's say the initial position is down here. The x graph is the integral of the velocity graph. So if I take these 2 points, say, I can apply the kinematic equations. Let's say I can apply the first kinematic equation to determine what my x final will be over this interval. Boom, I use my first kinematic equation to determine my x final over the interval, given my known x initial, yada, yada, yada. And it'll end up at some value for which I'll have a parabolic curve connecting them. Boom, parabolic curve connecting them. The curve here is concave up because velocity is increasing, or another way to say that is the slope is increasing. So that's why it'll look concave up. In the second section, it'll again be a parabola. This one's much steeper though, which I'm kind of sad that I've drawn it so short here, but it'll be steeper in this second section because we've got a steeper velocity slope. So let me try redrawing this a little bit more prettily, and then we'll call it a day. So I've got, say that I do that calculation, I find that my final point is there. Over this interval, I find my final point is like way up here somewhere. It'll be a nice, smooth parabolic curve, the tightness of which will be determined by the slope of the velocity graph. Okay, I know I kind of zoomed there at the end. There's kinematics and these kind of acceleration, velocity, and position graphs in a nutshell. I've kind of got my x graph running up into the velocity graph. That's pretty funny. X, t, t. Everybody's on the t position here. This is for the special case of constant acceleration. So for the constant acceleration graphs, velocity forms straight lines, positions form parabolas. And I can determine the endpoints for each interval using my kinematic equations.
So, sorry, not to cut you
Go
off.
for it. You're good.
Just for your velocity graph, so do you have 2 different sloping lines, basically, that are connected?
Yeah, so these would be 2 lines that have different slopes. My first line has slope 1. Slope equals 1, because the acceleration has a value of 1 there. This second section should have slope 4, which I've drawn it a little bit underemphasized. There we go. Slope 4, because acceleration there is 4. Does that help? Is that okay?
Yeah, it does. Thank you.
Yeah, good stuff. All right, so without further ado, I'm going to go ahead and end the recording.